This is the next video in a chapter on chemical bonding and molecular geometry. We are going to do more advanced Lewis structures now, where there's multiple structure options, so we need a few more tools to help us decide which structure is going to be the most stable. Those tools are going to be formal charge and resonance, and then we'll talk about exceptions to the octet rule. As we start this new section, we need some new tools. Need some new tools that will help us choose the best structure when more than one structure is possible. And now I'm talking about two legal structures. In our previous video, we drew a couple of different structures here for C2N2, and we crossed out this structure specifically because it didn't, this carbon wasn't in the center, and we crossed out these structures because we didn't have complete octets. So these are not multiple options, those are illegal options. I am talking about multiple legal options that could happen, and we need to decide which one is the best. So the first tool we're going to use to help us decide is called formal charge. And formal charge is like assigning a hypothetical charge to each of the atoms. So it's the hypothetical charge of the atoms if the bonding electrons were shared equally, meaning that there's one electron belonging to each atom in the bond. As you might have guessed, there is another type of charge we can assign that assumes unequal sharing. So the way I remember that formal charge is equal sharing is that formal charge is formal. So in a formal setting, you're on your best behavior and you always play nicely with others. And so you share your electrons equally with your partner. So we're going to abbreviate formal charge as FC because we're going to be calculating it a lot. And the way we calculate formal charge is we take the number of valence electrons a particular atom had to give at the beginning, and then we observe where those electrons went. So some of those electrons still belong to that atom because they live in lone pair electrons, which only belong to one atom, and the rest of those electrons went into bonding. And if we assume that each of the two atoms in a bond shares the two electrons equally, then each atom gets one electron per bond, so we can just subtract the number of bonds. And that will tell us how many of those negative charges hypothetically belong to each of the atoms. And we can check our work to make sure that our simple math was done correctly by adding all the formal charges together. The sum of all the formal charges of all the atoms in a particular molecule should equal the total charge of the molecule. Most molecules don't have a charge, and so then the sum would equal 0. But if there is a charge on some sort of an ion, then the sum of all the formal charges should equal the real charge of that ion. So let's look at an example and put our skills to the test. So carbon monoxide has a couple of different possible Lewis structures. One of the possible Lewis structures has double bonds between each of the carbons and the oxygens, and two lone pairs on each of the oxygens. Another viable option would be a single bond between one carbon-oxygen pair and a triple bond between another oxygen-carbon pair, with the single bonded oxygen having 3 lone pairs and the triple bonded oxygen having 1 lone pair. So let's look at the formal charges for each of the atoms on these molecules as a tool to help us decide, which molecule might be the one that really exists. So I'm going to do my math over here below it. So this is supposed to be an O for oxygen. Oxygen has 6 valence electrons because it lives in group 16. We're going to subtract the number of lone pair electrons. So there's 2 lone pairs. So we'll subtract 4 lone pair electrons. And then we'll subtract the number of bonds. So this oxygen is bonded twice to carbon. So that gives us a formal charge of 0. And we can see that both of these 2 oxygens are in the same environment. They both have 2 bonds, and they both have 2 sets of lone pairs. So this calculation that we did is sufficient for both of those oxygens. So we'll go ahead and write that in. I'm going to write FC so that the person looking at this page knows what the heck I'm writing, why I'm writing numbers here. So each of the oxygens is going to have a formal charge of 0. So then we'll do carbon. Carbon has 4 valence electrons normally because it's in group 14. Lone pair, it does not have any lone pair electrons. So 0. And the number of bonds, it has 4. 4 minus 0 minus 4 is also 0. So every atom in this molecule has a formal charge of 0. And you'll see that most of the molecules that you work with, many of them will contain formal charges of 0 because 0 is the most stable formal charge to have. But not all of them will. So over here, let's do the calculation for this oxygen on the left. And you can see that these 2 oxygens are in different environments. So I'm going to have to do the calculation twice. So I'm going to label one oxygen A and the other oxygen B, just so it's really clear to myself which one I'm talking about. So for oxygen A, oxygen always has 6 valence electrons. It has 2, 4, 6 lone pair electrons, and it has 1 bond. So it's going to have a formal charge of -1, which is possible. We are looking for positive, negative, or 0 formal charges. Let's do the carbon next because it's the next one to the right. Carbon has 4 valence electrons. It does not have any lone pair electrons around it. And it has 1, 2, 3, 4 bonds in this molecule as well. So its formal charge is 0. And you can see that I'm writing 0 as an O with a slash through it, so you can tell when I'm trying to write 0 and when I'm trying to write O for oxygen. And then we'll do oxygen atom B. All oxygens have 6 valence electrons. This one has 2 lone pair electrons and 1, 2, 3 bonds. So 6 minus 2 minus 3 is a formal charge of +1. So we can see that the formal charges for the 2 oxygens are different. The carbons are the same, a 0 in both cases, but in the left molecule, both of the oxygens have 0 for their formal charge, and in the right molecule, 1 oxygen is a -1 formal charge, and 1 is a +1 formal charge. So that brings us to the question, which Lewis structure is best? Now that we find the formal charge, how do we use that information to make a prediction about which molecular structure is the most correct? So let's add a couple of rules here to help us choose the best Lewis structure. And of course, what we're doing here is predicting what the Lewis structure is. The true answer comes from experimental data. So we are going to choose the best structure by choosing the structure that meets as many of these 3 conditions as possible. So we want the structure where the formal charges are as small as possible. Small meaning the number. So -1 and +1 both being small, -2 and +2 being larger. So ideally we want them to be 0. But if they can't be 0, we'd like them to be ±1. We want to choose the structure where negative formal charges are on more electronegative atoms, because they are better at holding electrons, and the reverse is true, where positive formal charges are on the less electronegative atoms. There we go. And our third recommendation is we want to choose the structure where adjacent formal charges are both zero or are of opposite signs. So we don't like to choose structure where there are two positive formal charges next to each other or two negative charges next to each other. Those are particularly unstable. So let's go back to our structures and try and make a decision knowing what we know about the most favorable structures. We're looking for formal charges that are as small, as close to zero as possible. That would make more sense, wouldn't it? Let's call that as close to zero as possible. So our first structure has all zeros, and our second structure has zeros and ones. So that makes me lean towards the left. We're also looking for negative formal charges on electronegative atoms, which we do in this oxygen, but not with this oxygen. And adjacent formal charges are zero or opposite signs. That's okay. But the first rule makes it obvious. This Lewis structure on the left is much more likely, much more stable. So we're going to put a box around this one. This is going to be the predicted Lewis structure. And just to prove why we have those rules in the flowchart, remember there was a rule that told us that carbon was always a central atom and never a terminal atom. Let's see why that is. Let's try putting carbon as a terminal atom. We'll put the carbon on the outside, we'll put one of the oxygens on the inside. We can make the Lewis structure super fast. It'll look pretty much the same, just with carbon in a different place. And we'll label the oxygens differently because these are two different types of oxygens now. Let's try checking out the formal charges for these. So carbon has 4 valence electrons. It has 4 lone pair electrons, and it has 2 bonds. That gives it a formal charge of -2. For oxygen A, it starts with 6 valence electrons. It does not have any lone pair electrons, and it has 4 bonds, leaving it with a formal charge of +2. And for oxygen B, starting with 6 electrons, it has 2, 4 lone pair electrons and 1, 2 bonds, leaving it with a formal charge of 0. So our formal charges were -2, +2, and 0. So what do our choosing rules tell us about this? We want all the formal charges to be as close to 0 as possible. We have both a -2 and a +2. So those are pretty high formal charges. That's a pretty unstable molecule right away. We're looking for the negative formal charges on the electronegative atoms and the positive formal charges on the less electronegative atoms. Right away, carbon is usually our least electronegative and it has a negative charge. That's no good. Oxygen is one of the most electronegative atoms that we know, and that has a positive charge, so that's no good. This oxygen is okay. And then adjacent formal charges, 0 or of opposite signs, that part's okay. So we have a negative next to a positive formal charge and a positive next to a 0. But both of those first 2 recommendations are violated for this structure. So we really do not like this structure. It is very unfavorable. Too high energy. And so this is why we always recommend that carbon be considered a central atom, because carbon has an unfavorable formal charge when it is listed as a terminal atom. So that's how we use formal charge to make decisions about which of several possible legal Lewis structures is okay. In the next video, we'll learn about our second tool, resonance.